This is sessions 8.2, integration by parts. So besides the basic integration rules, we have new ways to integrate functions. Now that works only when we have two parts. Okay, so you should identify two-part function. So basically, the products of two functions. So before we get there, let me show you the where the formula comes from first. Okay, so looking at the product rule. Okay, so let's recall. When you take a derivative of f times g, f of x times g of x, it's f of x times g prime plus g of x times f prime. So the first function times the derivative second plus the second function times the derivative first, right? So that's a product rule. For example, if you want to find the derivative, okay, what's the derivative of x times sine of x? And using the product rule, okay, so using the product rule, what do we have here? The following the rule, we have x, right, times the derivative of the sine, so that's times cosine of x, right, plus, and then g of x is sine of x, is sine of x, then you times the derivative of f. Derivative of x in this case is 1, right? So if you take a derivative using the product rule, then we have x cosine plus sine of x times 1. Okay, so let me clear that. So that is the answer. Now let's imagine instead of finding derivative, we're talking about antiderivative. How do we find the indefinite integral of x times cosine x? Okay, x times cosine x. Notice that when this is the product, the thing will be much difficult to do it. Okay, you imagine if we only have a plus sign in between. You see, it's a different story. Let's say if you just have what's a different integral of x plus cosine x. Now that one is 10 times easier actually, because I can find the entire derivative x with the entire derivative x, so that's x squared with 2, and then that is for the entire derivative cosine, that is sine of x plus c, and we're done. See that? If you take the derivative of the right-hand side, definitely give you back this functions. But when you have multiplications, that's where it becomes hard. Okay, every time you have a product of two functions or a quotient of two functions, things doesn't work as simple as you might think. Some might believe, well, that is what? Oh, I can do that. It's x squared over 2. And then time, then that derivative cosine, this is sine of x. And then plus constant. The answer? Well, no. Why? Because this is a product. So if you take a derivative of this side, okay, what do? You actually take, use the product rule. You take a derivative, this one times derivative sine plus the sine times derivative x over 2. And then you see that when you do that, it won't end up with this. So that will not be the antiderivative of these functions. So in other words, you cannot take this part, integrate, put it together like we did with summation. With sum. Okay, so keep that in mind. So we cannot do that. Then what should we do? Well, here's a clue. Since we have this up here, you see that the x cosine x. See that x cosine x. So here's what we're going to do. Since I want to take advantage of what we know up here, if the antiderivative x cosine x, that's what I want to do, right? why don't we use this equality here, okay? And let's say integrate both sides of this equality, right? So what happens? If you take the antiderivative of both sides, now the antiderivative kind of cancel out, right? You take the derivative and take the antiderivative. That basically back to x times sine x there. And then the antiderivative of the right hand side, this is the sum. So that's the same as antiderivative x times cosine x plus, oh, this is dx, plus the antiderivative of sine x times 1. Or just sine x, right? I can do that. And then as you can see, now you have the antiderivative x cosine x dx there, which is that. If you subtract this over, then you would have x sine x times sine x minus the integral of sine x. Okay, sine x. Now do you see this integral turn out to be x sine x minus this integral? This integral now is just sine x. I can integrate that with no problem, right? So that's x sine x minus what's intended of sine? It's negative cosine. So it becomes plus cosine of x plus c. So what I want you to focus on is this one right here. It's equality. Okay, notice that this is actually come from the product rules here. And if you observe carefully, you should see this x is the same. The relationship between the cosine and the sine, well, the sine is antiderivative of cosine, right? Okay, so that part. And then you should have the one there. The one here is the derivative of x. So in other words, we might be able to develop a formula here where you want to integrate the products. That turn into this, where you have one term without integral, one with the integral. Hopefully that one we can integrate more easily. Okay, so let me redo this with a more general term. Okay, so instead of the x cosine x, let's see here. Okay, let's do it again. Here's the product rule, right? And then integrate both sides, right? So if you integrate both sides, that means I switch the order so that it'll be hard to follow. So if you integrate the left and the right hand side, then what happened is, you see this side, I switch so it'll be your left hand side there. Okay, right and left hand side. Then the derivative and antiderivative cancel out, that becomes fx times g of x. So flip the equations. Okay, so we get that. Then the next step is we integrate what, so this is sum, so I can distribute it in. So that means the antiderivative of the first term plus the antiderivative of the second term. Then we're gonna subtract this, so we move this over the right hand side, it becomes the minus, the minus sign. Now this is what we have earlier. Instead of integrating f times g prime, we have this equality f times g minus integral g times f prime. So basically the problem kind of switched from integrating f times g prime and up switching to integrating g times f prime. And hopefully that integral is easier to do. Okay. Now, that formula here is called the integrations by part formula. Okay. So you're going to need to memorize this one. However, to make things a bit easier to memorize, I think we switch notations here instead of using F, F and G. So we think of the F is U. So basically, this is letter U. This is the letter V. Okay. Then this is the V. And then this is the derivative of U, so be du. So you're going to have the variations of this formula, in fact, and we prefer the following, which is, again, you should see the same formula, switching letter, it make it look short. So you have the integral of U times dv, that's a derivative of V, equal uv minus the integral of v du. So that's how I read. The integral u dv equal uv minus the integral of v du. Now this again called integration by part formula because you will need to identify the two parts in the integral. So from here, this is the one part u and that's dv. So you need to figure out part 1 and part 2. One is u and one is dv when you integrate. Okay. Now, how do we identify u and dv? Okay. So if you go back to this example here, right? If you want to integrate x times cosine x, which one is u? Which one is dv? Now, you have two functions here, and apparently one of them is u, the other one is dv. So is that uses x or uses cosine x? All right, so that's what you need to think about. For now, I'm going to give you the simplest way to identify that. I call it the technique for dummy. Basically, you don't need to understand why for now. You just memorize, okay? Just pure memorization, okay? Keep in mind that the integration by part, this formula comes from the product rule for the derivative. So essentially, this is a product rule for integration, but it's much harder than the product rule for differentiation. Choosing u and dv takes some practice and experience. Now I'm giving you this acronym, LIPIT. So when you choose your u in the functions, you choose in this order, LIPIT. L stands for logs, I stand for inverse trig, P stands for polynomial, E stands for exponential, and T is for trig functions. So do in this order. If you look at the function, you see the log, that will be your u. If you don't see the log, then you try to look for the inverse trig, and etc. So I'm going to give you some example here. So here, the log function, you are looking at maybe natural log of x, right? Or maybe you have the natural log of 3x plus 1, okay? Or sometimes you have the log with other base, the log of 3x, say. So those are log functions. For inverse trigs, you often see the two types, the arcsine, right? So you might have the arcsine of x, or maybe you have the arctangent of x. So these are the two common ones. And of course, you might have arc, like side of not just x, or maybe 9x, x side of 9x, arctangent of 2x. etc. Okay. Then the next thing is the polynomial. So what polynomial? Polynomials, well, x squared plus 3x, right? That's a second degree polynomial. Sometimes you have just 2x, that is a first degree polynomial. Or sometimes you just have even 4, that's a constant. That's still considered polynomial with degree 0. Okay, or maybe you have x to the 6, right? So that is still polynomial. Okay. Now, or power function in general, power polynomial. And for the exponential functions, you often encounter e to the x, right? Or you may have 3 to the x, or be e to the 2x, or even sometimes you can have a 4e to the negative x, right? So those are exponential functions. Now, trig, you're going to see most likely the sine and cosine. So sine of 2x, cosine of 3x, etc. So these often just sine and cosine. I don't think we have tangents involved. So sine and cosines are the most frequent one you're going to see. Okay. Right. So again, look for these functions as you determine what is u. Once you identify the u, the other part, okay, the remaining part will be dv. Okay. So let's look at the next first example. Okay. I'm going to look at example 1, which is, I think it's the same example that we had before. Okay. X cosine x. Now I'm going to do the formulae. Now, if you look at these, you should notice that the x times cosec is the product of two functions, and again, what you have is that is Lipet, L-I-P-E-T. So you look at this, what type of function is it? X. And what type of function is it? Cosine x. Well, cosine is trig. X is this, right? Polynomial or power, whatever you want to call polynomial power, polynomial function. So that's P. Since P comes before T, then you will let U be X. Okay. So again, here's our integration by part formula using a Lipet. That is a polynomial factor. That's polynomial factor. And this is what we're going to let U equal X. Okay, U is X. Now, once you let U be X, then what's dV? dV will be the remaining part. Okay, so if you identify U, dV, so that's your dV, including the dx. So keep that in mind. dV will be cosine x dx. Okay, dV is cosine x dx. And then in order to apply the formula, look at the formula here, that will be equal to what? U times V. U times V. So you need to know V. You need to know V minus integral of V du, and you need to know du. Well, du is just a derivative of u. So that's why in order to apply the formula, you need to find the derivative of u. What's the derivative of these functions? Or in other words, what's the derivative of x? Well, it is 1. I didn't put it there, but it's 1. Derivative of x is 1. Okay, so keep in mind that when you take the derivative of u with respect to x, then derivative of x here is 1. and you multiply both sides by dx, so you do it in the differential form. Okay, so du dx is 1 times dx on both sides, and that's what you got. Now, on the other hand, dv is cosine x dx. That means the derivative of v is cosine. What is v? So given derivative is cosine, you find v, that means you're going to find the antiderivative. So what's the antiderivative cosine x? Sine x, right? So v is sine x. Okay, so when you have that, then you get ready to plug in the formula. Again, that's equal u times v. You take u times v minus the integral of v. V is sine x times du is 1 dx. Right, so that's equal this. Okay, so our original integral, that one, would equal uv minus integral v du, and let's plug in. Plug in. You see, u is x, v is sine x, minus integral v is sine x, du is 1 dx. And then from here, you see that is x sine x minus integral of sine x dx. So you only need to integrate the sine x, which is negative cosine. So your answer is x sine x plus cosine x plus c. So do you notice that this is the same answer we had earlier, right? In the very first example. We did that, delete it. Okay. So that's the same answer. All right. Now let's look at the example 2 here. Now in this example, we have ln x dx. Again, we're using integration by part. When we talk about integration by part, we have 2 parts. So you expect it to have 2 functions, a product of 2 functions. Then you're like, we only have natural log of x. We only have 1 part, so what's the other part? Well, you can always think of that is the same as ln x times 1 dx, right? So we do have 2 parts. This part right here is, of course, is the logarithmic factor. That's log. And the 1 is a special case. If you look at what we have down here, it's still considered. So we have the log and the constant for the 1. That's polynomial. So this is really the log. This is really the polynomial. The L comes before the P, right? So you let U be natural log of x in this case. Okay. So again, using the Likert rule, this is logarithmic factor. So we let U be natural log of x. And dv is, well, I would like to put it as 1 dx here to be precise, right? So log of x is u, and that's dv is 1 dx. And as before, we need du, so you need to take a derivative of u, or derivative of natural log of x is 1 of x. So du is 1 of x dx. dv is 1 dx, so that means the derivative of v is 1. What is v? So you see, we got to do the antiderivative, and that is x, right? Derivative of x is 1. So when I have the everything I need, apply the uv minus integral of v du formula, right? So u times v. This time the u is natural log, the v is the x, minus the integral of v is x, and du is 1 over x, right? So we kind of apply the product rule for the integral and call the integration by part formula, right? So after you do apply the formula, what's next? Well, we have this ln x times x minus here you see that's the product, there's still product there, but I could simplify, right? I could simplify from here because that's cancelled, you're left with the 1. What's antiderivative 1? Well, the antiderivative 1 is x. So the answer I have here is right. So the answer I have here is x ln x, and antiderivative 1 is x. So that is the final answer. Right. So let's look at the next example. Okay, the next example here we have what we have x squared times e to the x. Now x squared times e to the x. Well, so what type of function we have here this time? What is x squared? What is x squared? Well, x squared is this one, right? It's a polynomial. So we have a polynomial. What's e to the x? That's exponential. Well, p first, right? So we're gonna let u be the x squared. Okay. So if you let u be x squared, and okay, here's the formula again. Then we have u be x squared this time, and dv will be again e to the x dx, the rest. Okay, we have 2 parts. Once again, for the u, you need to find du, or derivative, it's 2x. For the dv, you're going to find the entire derivative. The entire derivative e to the x is e to the x. So v turned out to be e to the x, the same. Apply the formula. You have x squared times e to the x, u times v, minus integral v is e to the x, times du is 2x dx. Now, let's rewrite this a little bit. Take the 2 out and rearrange it. I have a new integral to do. The first 2 examples, we were able to integrate this function with no problem. This time there is an issue. Why? Because you still have x times e, right? There's multiplications there. And since there's multiplications there, we cannot do, and we're gonna use other techniques. What techniques? Integration by part again. How? Because there's a product of x. What is x? Polynomial. What is this? Exponential. So you see a polynomial exponential again, p and e. So you can repeat that with the integration by part the second time. Right? So from here, we have the product, and we need to use integration by parts again. Right? So that u be x this time, dv is e to the x, and du is dx. V is e to the x, but antiderivative, and that's the derivative. Right? So here again, if you want, you may want to put down it's really 1 dx. Apply the product rule, the integration by part rule, u times v minus integral v du. So this time we have, let's see what we have here. See that one is the same. The integral here using integration by part. This is u, this is the v minus the integral of v is du. Now that one's much better now because you only have the entire e to the x left, which I can integrate, right? Entire e to the x is e to the x. At the same time, you can multiply and distribute. I think we got the answer immediately. After you multiply in, that's negative 2 e to the x, 2x e to the x, negative positive, times 2, right? And then times e to the x is e to the x. So that'll be the answer for that. So notice how we applied the integration by part twice. Okay. Now think about this. If we're gonna have to do this, why do we have to do the integration by part twice? Look at the product here. When you apply the integration by part, you change this integral to another integral. This integral, you see this one has a degree because the polynomial, when you take the derivative, x squared becomes 2x. So the power go down once from x squared to x, but you still have product. And so that's why you're using the part again. When you derive the x become 1, then there's no more x. And with only one function that can integrate. So you see that how the power, in this case, we get the power function times the exponential. You got to do twice to get rid of the x squared. If you imagine if we have the x to the third power or fifth power, that means you're going to have to do it 3 times and 5 times to keep bringing that power till it's gone. Okay, but we're going to do this. Well, it's not so efficient, especially when you have third degree or higher, where you can do it 3, 5, 10 times. So we're going to want to develop a shortcut. But in order to do the shortcut, you need to observe this problem carefully. I mean, the answers. Okay, if you look at the answers here, you notice that how the x squared go to 2x. To 2x, right? So the root of x squared is 2x, and then there's down to 2. I could take up the 2 there so you don't see. So you see that the 2x is derivative of x squared. The 2 is the derivative of 2x. Okay, now the e to the x doesn't change. In fact, the e to the x does change though. It stays the same just because the antiderivative e to the x is e to the x. Antiderivative e to the x is e to the x. So you should expect to see this part is antiderivative of this. That's antiderivative of this. So if you have a third degree, you know that you're going to have to take the derivative and derivative and derivative. The second part is going to be the antiderivative, and antiderivative. And then the sign here, you see that it cuts positive, negative, positive. The reason is switching around because of the integration by part rule with the negative here. So it's negative. When you apply it again, because there's 2 negatives, so turn into positive. So the sign would change. Okay, and as I observe the patterns, that leads us to the following observations. Okay, and the rule. Okay, so let's redo this with our observations. I'm going to write f of x and g of x. So assuming the f of x is the first part, which is that one, okay, the derivative, g of x is the e to the x in this case. And what it would do is start with x squared, and take a derivative, 2x, second derivative, 2, take a derivative, 0, okay? The other function e to the x, you're going to find the integrals or antiderivative. In this case, it's change e to the x. That's e to the x. That's e to the x. And then the sign will be alternating positive, negative, positive, negative. So notice that we have x squared. Actually, the original one doesn't use in the formula. So it should be x squared times e to the x, then 2x times e to the x with the minus sign, and 2 times e to the x with the positive sign. You see, that's how the answer we got. So that's how we're going to do. Find the derivative, find the antiderivative, put in the sign alternately, positive and negative, and you can multiply in diagonal, basically, this pattern. Okay? And then this will give us what we call the shortcut, and we call it tabular integration. All right, so let's look at this one here. So, okay, tabular integration work for integral of the form. If you have to integrate to function, right, f times g, where the function here had to differentiate to 0 several steps. Normally, the power function, so the polynomial, when you take the derivative a few times, it should be 0. And then the g of x should be easily integrated, and it could integrate repeatedly, like exponential functions. Okay, so look at this function. Here's another one that works with the tabular integrations, where you can see the polynomial here can differentiate a few times, become 0. The sign I can integrate easily. Anyway, you go from cosine to sine. So let's see how that works. All right, so start with the f of x, x cubed, take a derivative, 3x squared, again, 6x, again, 6, again, see, 0. Well, you need that to get to 0, otherwise you go on indefinitely. And then for the function g of x, second one, sine, right? Take an antiderivative. Remember, antiderivative is negative cosine. The antiderivative, negative sine. The antiderivative negative sine, cosine. Antiderivative cosine, sine. So I stop here because that's in 0. So we're going to start with 2 columns. And then don't forget the sign will be positive, negative, positive, negative. And we're going to go down diagonally so we don't use the first one. So that one times that one. Okay, x cubed times negative cosine. Okay, x cubed times negative cosine. So you see that. And then negative 3x squared times negative sine. Got positive 3x squared sine x. Plus 6x times cosine. Then minus 6 times sine. And then you add the constant. And that's the answer. Now, if you don't remember these integrations or tabular integrations here, you could still do it with integration by part, but notice that it's a third degree, so you'll be expected to do integration by part 3 rounds. Okay, so basically just a shortcut of by part 3 rounds, right? Let's finish the first part of integration by parts.